Hello, I'm Bart Klumpers. I'm a research developer over at SCM. We are a software company that focuses on the development of simulation tools for chemical systems, which includes OLED devices. So during this talk, I mostly want to focus on giving you an overview of our modeling capabilities and show you how we can use this modeling to assist and accelerate your research into new OLED devices by bridging the gap from molecular properties all the way to the device. Now, an understanding of how OLED devices work is necessary to perform an informed design. While it is possible, certainly, to do a brute force experimental screening, this approach is very slow and expensive and not really something that we do anymore in the modern day. So in order to get an understanding of how OLED devices work, we really need to consider the molecules that make up the panels. And quantum chemical methods are the de facto method that has been used for quite some time to perform this studying, and also perhaps what we as a company are most known for. So using techniques such as DFT, we can use this to estimate molecular parameters such as band gaps or the conductive properties. However, we also need to consider not only the individual molecules, but also how these molecules behave inside of the film. The environment of the molecules results in molecular interactions, and this causes shifts in the energy levels, shifts in the color spectra, and also has an effect on how electronic transport between molecules occurs, and therefore how efficiently we can get electrons from our electrodes to our emitters. Finally, we also need to consider how the different layers are stacked inside of the actual OLED pixel in order to look at the distribution of charge carriers between the layers, looking at the buildup of charges, looking at how different charges interact with one another, and if there are any transport limitations in getting electrons to the emitters. Once we know what the multi-layer stack looks like, we can then trivially scale that up towards pixels or panels to get the full picture of the device. First, we will focus on the molecular side, where we can use techniques such as DFT, which we have implemented in our ADF package to characterize emitters. One key example of this, which has been frequently used, is in studying how we can optimize emitters, either focusing on optimization of color or focusing on the optimization of its emissive characteristics. Emissions involve an electron injecting into the emitter, causing an excitation, which can then decay in order to result in the emission of light. And theoretical screenings allow us to then search for emitters that have the desired lifetimes, such as those in phosphorescence, to result in slow decay pathways without having to go through all the extensive process of designing syntheses for each of these individual molecules. We can also combine this information with studies into things like intersystem crossing rates, if we're interested in TADF complexes or distribution of different spin states, or the study of charge transfer processes in order to see how these materials interact with their environment. In addition to simply the molecular properties, these purely electronic properties, we also obtain emission spectra, and this is one of the things that has been a big focus in, for instance, the search to blue emitters. This approach has been shown to work relatively well for a wide range of molecules in comparison to experiment, and this provides one of the main advantages here, in that we can get information in terms of which portions of the molecule are actually responsible for the different features of the emission spectrum, and therefore we can use this information in the design of new ligands by focusing on tweaking the specific bonds that produce these different peaks or different parts of the spectrum, allowing us to shift them around, changing their intensities, etc. However, we need not only consider the individual molecules, but also their environment. Because the environment will ultimately have an effect on the actual shape of the emissive spectrum due to either a broadening due to environmental interactions, shifts in energy levels causing shifts in peaks, and so on. So to characterize this environmental effect, we have implemented two different workflows. On the one hand, we can perform a simulation of chemical vapor deposition to really get an atomistic picture of the complete morphology. So this is the approach that provides us with by far the most detailed picture of the environment. So for each molecule within this morphology, we can then go and calculate all of its electronic properties. We can calculate the transfer rates of individual molecules to all of its neighbors in order to characterize also the disorder in these parameters in the film. Because we have an amorphous solid, we do not have a perfect crystal. It means that there's going to be variations in these properties between individual molecules, and these variations can result in a broadening of our emissive spectrum. It can result in the formation of different trap states and other such processes. So these are things that we want to be able to characterize in order to fully understand the processes in the OLED. However, when we're performing something like a molecular screening, we don't necessarily always want to get this high detailed information, and instead want to get a quick estimate of the environmental effect on, for instance, the shifts. And so we can instead utilize things like semi-empirical methods combined with embedding approaches to very quickly estimate what the environmental effect is, how energy levels change, how potentials change, and these properties, while not necessarily as accurate, can be used as a first estimate to feed through to the large-scale models, and then to get an idea of which emitters that we have might actually be of interest to the actual device. And the materials that don't give good initial results we can ignore and then only use the high value candidates in subsequently more detailed studies. So this methodology of tackling different scales leads us to a multiscale workflow. For the molecules and the morphologies, which I discussed previously, we obtain this distribution of properties from the amorphous film, or by simply estimating the sensitivity to environmental parameters. We can also obtain distributions not only of things like energy levels and band gaps, but also the rates of certain processes in the device, such as quenching or annihilation rates. These properties that we obtain from the morphology is then used to represent the different layers in our OLED stack, which we can then go and study using mesoscale techniques such as KMC to obtain an idea of what the process characteristics are like at longer time and length scales. It allows us to include long-range effects, long-range electrostatics, the role of the interfaces, and this is all information that we can then use to determine parameters of the actual device, focusing on the efficiencies and the overall emission spectrum, and we also take into account optical losses. So the method that we have chosen for this is a three-dimensional kinetic Monte Carlo. What this means is that we are going to be tracking individual electrons as they move through the device. And this allows us to really identify which pathways the electrons use to move between the electrodes, to move from the electrode to the emitter, and to identify where possible diffusion limitations are, or where the electrons are diverted away from the emitter sites to form into trap states, to form into rapid transport from electrode to electrode rather than resulting in emissive events. It also allows us to identify how electrons interact with one another, how they engage in loss processes, etc. One of the main advantages here of the 3D kinetic Monte Carlo approach is that we're able to retain morphological information about the actual distribution of the molecules in the film. And this allows us to characterize also more complex systems. It allows us to get an idea of how the role of the dye distribution in a host-guest system affects the efficiency of the device. It allows us to look at polymeric materials. It allows us to look at how the proximity between dyes and sensitizers affects efficiency. And because we have a time-resolved simulation, it also means that we can go and focus on performing lifetime studies by incorporating degradation mechanics, as well as transient response studies to see how, for instance, voltage fluctuations or external factors can disturb the operation of the OLED. So compared to a continuum approach, the main advantage really of kinetic Monte Carlo is this morphological detail. Because we know exactly where the molecules in the film are located and the distribution of these molecules, we can also include the distribution of the molecular properties explicitly. So instead of simply looking at a homogeneous layer where we take an average of the different properties, we can specify exactly where in the device molecules with specific energy levels or molecules with specific emissive characteristics are located. And then we can use this to identify trap states. We can identify hotspots for localization of specific carriers or specific preferential filamentary pathways that direct the electronic transport and also result in the accumulation of perhaps certain regions where loss processes occur. Now, two of the main pieces of information that we then obtain from the kinetic Monte Carlo is on one hand the distribution of the processes that occur in the device, and on the other hand where in the device they occur and which materials are responsible. So if you're looking at a device that had a more complex OLED design which may contain many different components, we can identify the role of all of these individual materials. So here we're showing an example of a TADF emitter that we have looked at previously. And one of the things that we can identify for this is, for instance, the efficiency by which one of the things that we can identify here is how the distribution of our different carriers is distributed through the material. So we can see a mismatch in electron and hole distributions. We can look at the efficiency of the blockers, and most notably the buildup of charge at the interfaces, which is particularly notable for this system. So because there's an energetic mismatch in the specific blocking layers that were chosen for this system, we see a buildup of charge at the interface, which results in a high density of electron-hole pairs, and eventually also a dominance of quenching and annihilation mechanisms at these interfaces, which is reducing the efficiency of the device. And so the information about these processes, and therefore also the molecular processes that are responsible for this, is something that we can use to then optimize the stack design or the choice of materials that were used in the stack to further improve the OLED efficiency. Now, aside from focusing solely on the static efficiency that we see here, the other thing that we need to consider is also the long-term stability. So this is something that I mentioned earlier, and something that we can study by including degradation processes. So these degradation processes can either be electronic deactivation events or they can be some sort of chemical reaction. And these are processes that we can characterize using our molecular modeling strategies. And so when we include these processes in the simulation, we are able to now also correlate exactly where the events take place in the device and which specific optoelectronic processes are responsible for triggering these events. So in the example here, we can see that this buildup of charge carriers at the interface results in a very high rate of quenching events, and those in turn can trigger a permanent deactivation, and that results in a loss of emitters and therefore a loss of performance of the device over time. And this is also why we see that when we move to a higher current density that we see a more rapid deactivation, because we have a higher number of quenching events that occur in this system. Now, what this example shows us, or what we want to show with this example, is that when we focus on the design of OLEDs, we not only want to consider solely the efficiency or solely the stability of the device, but we need to consider multiple aspects. So you have the efficiency, you have the emissive characteristics, and you have the lifetime of the device. And if we modify the properties of the OLED in order to optimize the emissive characteristics, then we might have a negative impact on the degradation. We might have a shift in color spectra if we start to mess around with the distribution of materials. And so simulation methods provide us with a very efficient tool set to perform screenings of what these different parameters can do to the performance of the device, so that we can do simultaneous optimization of all these different processes, which is something that would be very expensive and very time costly if we wanted to do that using a purely experimental strategy. And this is also something where currently we're also putting a lot of effort into data-driven acceleration to kind of help in this high-level multi-dimensional optimization. Now, for those that are interested, we can also move past these micro-scale pictures, so we can go further by considering also the larger scale levels, which is something that we have done primarily using coarse graining approaches. What this means is that we can effectively subdivide pixels into the different nanoscale domains that we discussed previously, and then we can allow communication between these different domains in order to approximate the behavior of the larger system. And this is something that can be used to investigate variations between pixels in case that you're dealing with particularly complex morphologies, such as with PLEDs or multi-component systems, to investigate if there's maybe variations there between pixels, but also to identify long-term stability of your display quality. So how degradation might have a selective effect on specific parts of the pixel, specific parts of the display, which is something that has been used previously for the study of, for instance, burn-in in OLED panels. So now that we've kind of covered different multi-scale domains by focusing on the molecular side, by focusing on the mesoscale side, focusing on the morphologies, we can use this in kind of a ground-up optimization of our device. So this is an example system that we were a part of, where we start with some sort of known emitter. This is something that you typically obtain from a previous study or something that you know because it's an earlier product. And we can perform a molecular level optimization by focusing on, for instance, the color, by focusing on the lifetime, or even using some sort of heuristic to estimate what type of energy efficiency we expect from the type of emitter. Then we can use the information, the molecular properties, to start our mesoscale studies, to start device level modeling, and we use this to now optimize the lifetime of the panel by considering things like layer composition or the stack design. So in some cases we're able to nicely segregate the molecular properties for instance, emissive features, and then focusing more so on the device for optimization of efficiency, for optimization of lifetime, and other times these two are more interconnected, requiring you to kind of go back and forth between these two stages of the design. And that is also something that we do quite often. Alternatively, and something that we see becoming popular more and more nowadays, are also inverse design strategies. So in this case, we would actually start on the device level, where we would use, say, virtual materials to perform a screening of which types of molecules, what type of molecular features we expect to yield desirable OLEDs, and then use that information as kind of a target property for molecular searches. So once we know the types of molecules that we want, we can perform screenings, which we can either do using traditional quantum chemistry or semi-empirical approaches to look for desirable emitters or desirable host guest systems. We can do this by either focusing on things like ligand optimization, we can focus on the minimization of loss processes in the morphology. These are all different factors that we can then consider. And once we have candidates that we think are viable for this process, these can be verified using either experimental approaches or by putting them through the feed-forward strategy, by performing more detailed molecular studies, morphology studies before performing device-level simulations, and maybe also investigating a larger range of operating conditions, investigating the role of the device, and so on. So this is something that is currently also a big focus of development, a lot of academic interest, and something where also things like machine learning acceleration is becoming more and more prevalent to help accelerate both the molecular searches, the optimization of the stack design, which is something that we are currently working on, and the inverse design of moving from stack to molecule. So I'm hoping that this overview that I've given gives you somewhat of an impression of where the capabilities of modeling tools are, mainly as a tool to help you go through a large number of molecules, a large number of materials, with the multi-scalar nature of these workflows nowadays, allowing you to really connect the molecular properties also to the device level, where oftentimes the manufacturing and fabrication can take quite a lot of time compared to traditional lab scale experiments. So feel free to let us know if you have any further questions, or if there's anything else you wish to know. You can also check out additional information that we have online about our various different products, and I'm hoping that this information has been useful to you.